what.
Okay, thank you, Mario. Thank you. This very nice introduction. So, hello everybody. My talk today is inclusive breakup of lithium-6 on bismuth and some related topics. So this is originally begin with my thesis, PhD thesis in University of Sevilla with Antonio Moro. And after that, I continue working on that. I'm working on this in Ohio University. Right now, I'm working in INFM Pisa. So from the title, you see my topic is focused on lithium-6. So lithium-6 for me is very, very special. So why we choose lithium-6 to do the study? Because experimentally we know lithium-6 here, it is a stable nuclei. For a stable nuclei, which means that we can get a high beam intensity. So this is easy for experiment. It's very easy to perform the lithium-6 beam. And since this is very easy for experiment, then we can have some very high accuracy data for the elastic scattering, breakup, fusion, and income fusion. So this is a very convenient nuclei in the experiment. And also this is also very important nuclei in the theoretical point of view because lithium-6 we know is an alpha deuterium two-body cluster. And because of this two-body cluster, when the lithium-6 working on target, we can consider this as a three-body model. So in this, we consider this as alpha, deuterium, and target with this three-body model. So there is several problems I need to solve today. In this my talk, I will discussing about some inclusive alphas. For example, there is a interaction I discussed about lithium-6 on bismuth. In the experiment, they only detect the alphas. So only the alpha particle is detected. So here I show the data point here. This is an inclusive data with integrate all the angular part. So this is a data point. In the past, people doing the calculations, for example, they do the CDCG calculation, they do the CRC calculation, and they do the other calculations. They sum all the contribute components and try to reproduce the inclusive alphas. But in fact, they cannot reproduce the alpha. All the components, when they sum together, they get this line. So in addition, we show the CDC calculation gives alpha D breakup cross-section. The alpha D breakup cross-section is very small compared to the data here. We notice that this is a log scale, so this magnitude is different. So here, for our goals is that we want to theoretically predict the cross-section of these alphas, not only the integrated alpha, integrated cross-sections, but also the angular distribution. Here, this is alpha as a different energies, but we also need to know for each energy, it has an angular distribution for alphas. So as here in this paper, they discuss both data and also these calculations. In addition, I take some picture from Caitlin's talk. In her talk, he mentioned something about fusion suppression because about the weakly binding of the lithium-7. The lithium-7 has a alpha titan two-body cluster. Because the lithium-7 is not tightly bound, so one is connected, one is interacting with the target, it can break into alpha and break up into alpha and titan. So compared to the tightly bound nuclei, the fusion of the lithium-7 is suppressed because for the tightly bound nuclei, the single barrier penetration model can reproduce the data of the oxygen 18 very well, but not for the lithium-7. So we want to understanding what is the relation between the breakup and also the fusion, and also explain the fusion suppression of the lithium-7 or lithium-6 or all the other weakly bound nuclei. And in addition, we want to have a model to predict this fusion cross-sections. Not only explain why there is a difference, but also we need to a model to reproduce the fusion cross-sections. So we begin with the inclusive breakup of lithium-6. The inclusive breakup means we have the lithium-6 beam interact with a target. So in the experiment, only the alpha particle is detected. So from the experiment point of view, this is a lithium-6 induced reaction, only alpha particle is detected. So from a theoretical point of view here, this is a Joule function. Then it is a very easy relations. We need to know the asymptotic part of each channel, then we get the cross sections. So from the theoretical point of view, we have different contributions of alphas. They have different reaction channel can contribute alphas. I cannot list all of them, but at least some of these are important. So for example, we know lithium-6 is alpha plus D two-body cluster. So when it breaks, it can break the alpha and the deuterium, keep the target no change. So we can call this a three-body breakup because the internal structure of this three-body keep no change. Or we can also call this scattering because this internal structure of this three-body no change. In addition, the lithium-6 can also discussing by a three-body model, which is alpha, neutron, and proton. So here, this one lithium-6 breaks, they can break alpha, neutron, proton with the target. So this is kind of four-body breakup because the internal degree of freedom of alpha, neutron, proton, and bismuth is no change. So this is the kind of four-body breakup. In addition, we can have some other channels. For example, in the three-body case, we have the alpha deuterium breaks and also the target, excited target to some excited state, and can have the alpha neutron proton with some target excited state, and also have some transfer channel is transferring a neutron to the target or the neutron and the target for some compound state, which is called incomplete fusion. So in addition, we give some definition. For example, this is by using the three-body model, we can call this three-body elastic breakup. And all the other components, we can say this is three-body non-elastic breakup. Or we can say this is absorption. So because of the internal, the asymptotic part of wave function of the three-body is changed, this is absorption. Or we can also we can define the four-body non-elastic breakup by defining the four-body elastic breakup. In this case, the four-body elastic breakup and the three-body elastic breakup is these two is also we can define the four-body elastic. So to make this problem very simple, we try to solve this by a three-body model because three-body model we define this alpha, deuterium, and bismuth. So this is an overview of what is the inclusive breakup and what is the contributions for the alpha channels. So as I show here, they have some pictures trying to explain which different components, but in fact, they cannot reproduce the data very well. So there is some experimental example of inclusive breakup. As I said in the experiment, the lithium-6 induced reaction, only the alpha particle is detected. And also we saw that this alpha is much larger than the deuterium, which means that the elastic breakup is not the mini part. Because if the lithium-6 can break up to an alpha and the deuterium, this alpha and the deuterium should be the same. But here, alpha is much larger than the deuterium, which means there are many other contributions. In addition, there is some application called surrogate reaction. The more detail you can find in Andrew's talk and also the Utah's talk next week. So the surrogate reaction means we have some desired reaction like a neutron and a target for some compound nuclei. For some cases where this target is A cannot be served as a target because maybe it's a weakly bound or something. So we use the inverse kinematics using the deuterium as a target and A as a projectile. But during this reaction, they can form the same compound nuclei and decay with different mode. But here, this is kind of inclusive measurement because only the proton particle can be detected, and also these others is can detect by the gamma. So more detail, please focus on these two other talks. In addition, there is some application called knockout reaction. So more detail you can find in Angela's talk. The knockout reaction is also kind of inclusive measurement where the projectile interact with the target in some higher energy, like the oxygen-13 interact with the helium-9. They trying to study the oxygen-13 and neutron relative coordinates, the structure. So in this experiment, people trying to study the spectropic factors, and also current model is based on the semi-classical model proposed by Angela or some Ecknor approximation. So because only the model studied right now is using the semi-classical, so we need to a fully quantum model. The fully quantum model, we need to study this. So this is now I will discussing about what is the theoretical model, try to study the inclusive breakup or the part of non-elastic breakup. Because the elastic breakup part is very easy, because elastic part means the internal degree of freedom of three particles is no change. We only need to get the asymptotic part of wave function. They can be easily done by CDCC or Fadil. Maybe Fadil cannot be applied here, but CDCC is a good model to solve that. To study the non-elastic breakup part is very difficult because I list several components about the inclusive alphas. And if we try to compute each channel, and there's hundreds channel we need to compute, in fact. So this in principle, yes, we can do that, but in practical, no, we cannot do for most cases. So for that, in the 1980s, like almost 30, 40 years ago, people trying to discuss this, try to develop a model to solving the inclusive breakup. One group is called the Ichimura observation group. They're using a spectator participant model using the post-form T matrix. And on the other hand, the Udagawa Tamura group, they stress a breakup fusion model. They're using a prior from T matrix. In addition, Hosai and McCoy also using some other spectator model with some flashback projection. So they have three different groups propose three different models. But the problem is these three different approaches can have different predictions. So all these three models is quantum mechanics model, but the prediction is totally different. So our goal is try to find a suitable model for this inclusive breakup. Maybe one of this model is correct, or maybe none of this model is correct. Then we need to find a suitable model for this. And also, if there is one model is a correct model, we need to find a relation between these three models. But we have some challenge. The challenge means this numerical very difficult. As we see, this model is proposed in 1980s, but there is no numerical calculation between the after 20 or 30 years, even with a finite range DWA calculation. So this is numerical very difficult. We need to overcome this. So we start with the Ichimura observation model. We select this model as a starting point, try to study this inclusive breakup. In this model, it's a three-body model. So three-body means the projectile has a two-body cluster structure. One, it interacts with the target, only part of the projectile with a B particle it detects. So we don't know what happened with the X particle and A particle. So they follow any possible state between the X and A. So this is very difficult to understand what's the meaning of the any possible state. So let's do a simple case. For example, we consider the two-body case, not the three-body case. Now we focus on two-body scattering with some optical potentials. So X and A any possible state we can consider as a X and A two-body reaction. So in the X and A two-body reaction with the optical potential, we know it has the elastic scattering, which means the X and A, the internal degree of freedom no change, only the relative coordinates change. Or they have some absorption, or called reaction, or we can call the non-elastic scattering. They have some inelastic scattering. The X or A particle go to some excited state, or the breakup reaction, like X breaks into two or more fragments, or the transfer reaction, X transferring some particle to A, or the fusion reaction, X and A for some compound system, or the other processes. I cannot list all of them. So we need to compute the cross-section with the optical potential. This is very simple because by definition, the cross-section of the elastic scattering is related to the asymptotic part. So if we know the S matrix between the X and the A, we can compute the cross-section by using this relation. So the non-elastic scattering part of the reaction cross-section is related to the interior part. So if we know the wave function between the X and the A, we can compute the reaction cross-section by the expectation value of the imaginary part of the XA interaction with the wave function computed by this optical potential to get the wave function. By this integral, we can get the reaction cross-section. This is fundamental, so you can find this definition in any kind of reaction textbook. So this is defined in the two-body case. So the key point to study this tool is need to get the relative wave function between the X and the A particle. The asymptotic part gives the scattering, the interior part gives the absorption. So now we go back to the three-body case. The three-body case, if we want to get the absorption or the scattering, we need to get the relative wave function between the X and the A. So in the three-body model with the optical potential between the X and A. So for that, the wave function of XA is a solution of this kind of inhomogeneous equation. This inhomogeneous equation told you that this X particle is not a free X particle, which told you this is not free X particle interact with the target. This X is coming from A, coming from a two-body cluster of A. It's coming from A by some interaction, projecting this B particle out. So this is a short-term wave function, told you this X is not free. Because now X is not free, the asymptotic part is defined with some relation like S matrix with a Hanker function. So following the definition in the two-body case, the elastic part means the X and A, the internal degree of freedom, no change. We call the elastic breakup. This is related to the asymptotic part of the wave functions, and it's related to this S matrix compute here. We get the S matrix with some classic Gordon coefficient by defining the outgoing B particle and outgoing X particle angles. We get elastic breakup cross sections. So this is in principle equivalent to the CDCC method. The non-elastic breakup part, we call this is absorption. The absorption means we don't know what happened between the X and the A. It's an internal degree of freedom of X particle or A particle is changed. So this is the absorption part. Following the two-body case, if we have the wave functions computed by some potential here, and using the imaginary part of this potential, we compute the expectation value, we can get the absorption part. So this is the model called Ishimura oscillation model to compute the inclusive breakup. So the next thing, we need to apply this model to some physical case. But before we applying that, we have three-body model. The next thing, we need to define what is three-body Hamiltonian. So which means we need to have the two-body interactions. We can use the two-body interaction by using some optical potential between the deuteron and target, alpha and target. For that, we testing this by using a CDCC method. This is also a three-body method, which means we expand the three-body wave function by the ground state of the alpha deuteron in the lithium-6 or the continuous state of alpha deuteron. With this equation, we get a kind of three-body equations, and applying this two-body interaction in, and we get this three-body wave function. The asymptotic part gives the elastic scattering. So we compare this calculated result with some experiment data. The data is lithium-6 on, sorry, I forgot to write down here, on bismuth with different energy, like energy below the Coulomb barrier, energy around the Coulomb barrier, and also energy above the Coulomb barrier. So also we give a reference line of the optical model. Optical model means we use a two-body model. So this is lithium-6 and bismuth, we use a two-body model, and the CDCC a three-body model, we use alpha, deuteron, and bismuth, a three-body model. So to compare with the data, we find out the calculation agree very well with the data. So right now we have the two-body. This is just to testing the two-body interactions in the three-body case. We're testing the two-body interaction for these three pairs. And we find out we already has a model for the inclusive breakup, and also the two-body interaction is already testing here. So the next is trying to compute the inclusive breakup of bismuth. So for that, we're using a three-body model. In the experiment, only the alpha particle is detected. The data is come from this paper. So here, this is lithium-6 induced reaction on bismuth for different energies. and energy below the Coulomb barrier, around the Coulomb barrier, and above the Coulomb barrier. Here, this is a cross-section of detect alpha particles, and they detect inclusive alpha particles for different angles. So this is a cross-section as a function of angular distributions. So because we already compute we're using the CDCC method to test in the two-body case. And by using the CDCC method, we already have the elastic breakup part. So we put the elastic breakup part here, we find out the elastic breakup part is much lower than the data for all the energies. So for the non-elastic breakup part, we're using the Ichiro oscillation model. And to make this model calculation much simpler, we use a DWA approximation. So here, the blue line is the non-elastic breakup calculations. Here, if we sum these two, the elastic breakup and non-elastic breakup, we get the total breakup, which is the right line here. So here we find out that this right line goes very well with the data, not only the magnitude and also the shape of the data. So we solve the first question, how to reproduce the inclusive alphas, and also we find out this the component is dominated by the non-elastic breakup part. The elastic breakup part is only has some small contributions in these very small angles, or here, but the peak and the most contributions is come from non-elastic breakup part. So this calculation is saying that the Ichiro oscillation model is the correct model from these other two models compared to the other two models to study this inclusive breakup. So the next thing we have to first solve to the first question. The next question is trying to solve what is the relation between the breakup and fusion. For example, for a tightly bound nuclei, if there is a tightly bound nuclei when interact with a target from a very simple barrier penetration model, if this particle can penetrate this Coulomb barrier, then this particle can be absorbed by the target. This can be a picture of fusion. So if the projectile is a weakly bound, for example, the lithium-6 we are studying right now. So if the lithium-6 is weakly bound, when it penetrates the Coulomb barrier, the lithium-6 can break into a deuteron and alpha case. So not the whole projectile can be absorbed by a target, but only one part of the projectile can be absorbed by the target. There is a commutation between the breakup and also the fusion. So here, we define the two types of fusion. One is called a complete fusion. By definition, it's the total charge of the projectile get absorbed by the target, or the incoming fusion, only part of the projectile get absorbed by the target. From this very simple picture, we saw that there is a commutation between the breakup and the fusion. So maybe we can understand saying that the complete fusion is surprising due to the weakly bonding of the projectile, or we can say this is due to the breakup of the projectile. So for that, we can do a calculation. For example, we take the same calculation, lithium-6 and bismuth. We have the barrier penetration model calculation here, and also this is the CDCC calculation which can compute the breakup cross sections. If we say the breakup is a mean contribution to the fusion suppression, then we can say the barrier penetration model minus the breakup cross section should be reproduced data. But in fact, we did not see that. So this is the fusion data. By using these two very simple model, we cannot reproduce the data. There is still a gap here. So our goal goal is try to reproduce the data, but there is some challenge because we need to first understand the fusion suppression, not only from this very simple semi-classical point of view, but also we need to find a full quantum model. And also this picture should also reproduce the fusion cross sections. So in addition, we need to study about incoming fusion for the case here. This is a two-step process or one-step process. Two-step means the lithium 6 can first break up alpha and deuteron, then the deuteron get absorbed by the target. All the lithium 6 is kind of transferred to continue. Lithium 6, the deuteron is transforming from the ground state of lithium 6 to the continuous state of the target. So this is kind of what study about one-step or two-step processes. So let's first study about lithium 6 on the bismuth case. We're discussing about what is the reaction channel can contribute to the reaction cross-section to the lithium 6 on target. For example, the reaction cross-section there is some reaction channel like calling the electric breakup, which we discussed before. The alpha deuteron breaks, but the internal degree of freedom of 3 particle no change. All this, the internal degree of freedom target get changed. We can decide, we can call this inelastic breakup. Or we can have some transforming particles like transforming the deuteron to the target or transforming the alpha to the target. All this alpha and deuteron for some compound state or alpha and target for some compound state. So this is some income fusion or transfer reactions. So by definition, this is the non-inelastic breakup, but this non-inelastic breakup has two parts. One part is the B particle is absorbed by the target. The other thing is the X particle is absorbed by the target. In this case, it's a deuteron get absorbed by the target or the alpha get absorbed by the target. In addition, there is the fusion cross-section, and where the lithium 6 totally get absorbed by the target with following by some different decay. So in this very simple three-body pictures, we can write down the reaction cross-section as a compound complete fusion and elastic breakup and two pieces of non-elastic breakup. So please remember this very simple formula. Then we do a little massage of this formula. We write out the fusion cross-section is the reaction cross-section minus elastic breakup minus 2 part of non-elastic breakup. So we apply this formula to the lithium 6 on bismuth case around the Coulomb barrier. This is the energy of the lithium 6 on the bismuth. Here is incoming energy of lithium 6 as in the lab frame. So here we remind you the CF means complete fusion, NUB means non-elastic breakup, EBU means elastic breakup. We do the calculation for different channels. Like we first do the reaction cross-section, which comes from the CDCC model. This is similar as the two-body case, as the two-body optical potential here. The cross-section is the same. And also we have the elastic breakup calculation. We have the elastic breakup cross-section here. We have the elastic breakup cross-section. It's very small compared to the reaction cross-section. Then we have two pieces of non-elastic breakup where the deuteron is absorbed by the target, only alpha particle is detected. This cross-section is much larger and compared to the other components. Here, this is a cross-section for which alpha particle is get absorbed by the target, only the deuteron is detected. This cross-section is smaller than the alpha, includes the alpha contributions. In addition, we give the very simple barrier penetration model. And here we show that the barrier penetration model is much larger than the complete fusion cross-section. This is kind of fusion suppression. And we also know that the elastic breakup is very small, and the non-elastic breakup is very important here. And next, we apply this model here. We get this right line. The right line, first of all, we saw that the right line goes through with the data very well. So which means that by this very simple model, we can reproduce the fusion cross-sections. The data is come from the Das group. So the next thing we need to discuss about what is mechanics leading to the fusion suppression. I taking some plot from the Caitlin's talk. In her talk, she discussing something about the impact parameters about the different reaction channel, like the non-capture breakup has a larger B, larger impact parameters. The breakup capture has a smaller B. Because the fusion requires a smaller B, then she argued that the mean contribution to the suppression is coming from the breakup capture model. But from my calculation, this is not true. For example, this is the aggregate distribution between the L and the B smooth in the calculation. The aggregate distribution is related to the impact parameters. And here this is cross-section as a function of different L. So when we do the sum of the contributions, we get the reaction cross-section for the elastic breakup and non-elastic breakup. But this is a cross-section as a function of different L. We can consider this as a function of different impact parameters. In this plot, we show that the peak part of the elastic breakup and non-elastic breakup is the same position. So which means the impact parameter about elastic breakup and non-elastic breakup is the same. The only difference is the elastic breakup has a longer tail. For the large impact parameters, it has some contribution for the elastic breakup. So, but we need to understand what is a reaction mechanism to the fusion suppression. Here we use a toy model. The toy model here we try by hand changing the alpha D to body bending energy of the lithium-6 in the projectile. The physical value is 1.47. Here we change it to 0.47, 2.47, 3.47, and make it much larger. We do the calculation for the elastic breakup. We do the calculation for the reaction cross-section from the CDC calculation. This we see the cross-section is decreasing when the bending energy is increased. And also we also do the calculation for the elastic breakup. We show the same behavior, but the contribution of elastic breakup is very small. And also the two component of non-elastic breakup. So we apply the simple model as we discussed in previous slide, and by using the reaction cross-section minus the elastic breakup part and non-elastic breakup part, we get the fusion cross-section in this very simple model. So this model, we find that when it's become tightly bound, it goes well with, agree with the simple barrier penetration model. So in this very simple toy model, we find out the meaning contribution is coming from the non-elastic breakup part with the alpha production. Here, this is the most contribution part. So the next question, we need to understand why this cross-section is so important. So, for example, we want to study why this alpha production is important. Alpha production means that the deuteron is get absorbed by the target, and only alpha particle is detected. So in this very simple model, so the lithium-6 has a Coulomb barrier with the target when it interacts with the target. So this is a Coulomb barrier, and when the lithium-6 penetrates the Coulomb barrier, it can be breaks alpha deuteron or some other component. So the Coulomb barrier of the deuteron of the bismuth is this count. But because of the lithium-6 breathes the deuteron inside the Coulomb barrier, and if the energy is below the Coulomb barrier, but it still can interact with the target. This kind of Trojan horse effect. So we do a simple calculation. For example, we do the calculation for the lithium-6 on the bismuth case for different energy. We know because about the energy conservation, we know in these reactions, if the alpha particle breaks the whole energy, the deuteron with the target can be a low energy. So in this case, the deuteron and target is a continuous spectrum. So they can continue spectrum from 0 to incoming energy of lithium-6. So this is the calculation shown here, and this is the direct calculation by the lithium-6 by the deuteron and the bismuth. Here we show that the cross section is very small, with below the Coulomb barrier, but within the Trojan horse effect, or when the lithium-6 bring the deuteron in, we see that the deuteron has a larger cross section below the Coulomb barrier. So this is the meaning effect why the non-elastic recovery is so important, because of this Trojan horse effect. So the next question we want to study is called income fusion. From a very simple model about the income fusion, for example, the projectile has a two-body cluster structure. If the total of the projectile get absorbed, we call it complete fusion. But if the projectile first break up into two pieces, and after that only one part of the projectile is get absorbed. It's called income fusion. In this model, they can also call it breakup fusion, because first break up the lithium-6 in alpha and deuterium and then get absorbed by the target. So in the model that in discussing the Ichirao-Austin-Wilson model, the income fusion is only part of the nine-less breakup. For example, here, this is a reaction cross-section, which this is reaction channel contribute to the income fusion. This is nine-less breakup part. We need to subtract the other contributions, like the alpha D, the target go to the excited state, and also the deuterium get breaks into NP alpha, and all with the ground state and excited state on all the other channels. So in the literature, there is a different paper discussing about the income fusion, if this is breakup fusion, or here the title discussing about breakup fusion. And this is kind of two-body processes, similar as this picture. All this can kind of like transfer to the continuum, or the alpha particle transforming to the continuous state of the target. This is kind of one-step processes. So in the theoretical point of view, if we want to study about what is one-step processes or two-step processes, we need to know the deuterium of the alpha particle is coming from the ground state or excited state of the lithium-6. So if the deuterium is coming from the excited state of lithium-6 transforming to the target, we can call this is the two-step processes. First, the deuterium is excited from the ground state to the continuous state and transforming to the continuous state of the target. Now we can discuss in this kind of one-step processes. The deuterium is on the ground state of lithium-6 and directly transforming to the continuous state of the target. So this is a picture of the lithium-6 is first breaks into two particles, then the one particle is get absorbed by target. All this is kind of directly transferring a deuterium to the target, leaving the alpha particle escaped. And also we know the income fusion is only part of the nine-less breakup. Then we can study the problem of nine-less breakup, then solving the problem of the income fusion. So if the nine-less breakup is kind of one-step or two-step processes, we can see the left, the mean contribution of the nine-less breakup is a one-step or two-step processes. So for that, we're using a CDCC wave function in the Ichirao-Austin-Wilson model. This is a Ichirao-Austin-Wilson model. Like if we want to know the deuterium and target wave function, it's kind of a homogeneous equation for this one. And here we're using a CDCC wave function. Because CDCC wave function is so convenient, the convenient means that it is expand the ground state of the lithium-6 and the continuous state of the lithium-6, then separate these two components. So because we separate these two components, then we can get the contribution of the ground state or the contribution from the continuous state. In addition, because in our previous studies, we all of the calculation using the DWA, and also if we using the CDCC wave function, we can test in the validity of the DWA approximation. So for that, we do the calculation. We're using the CDCC wave function here. We consider the ground state and the continuous state. We're using the CDCC ground state wave function in itself, which means we solve the full CDCC wave function, but only apply the ground state part. And also we're using the DWA approximation, which we have is a product of the X internal, the lithium-6 ground state, and also the lithium-6 and the bismuth scattering state. We apply these three wave functions and to apply to the nine-less breakup. Here we find out the DWA is a very good approximation because DWA is this black line, the CDCC4 is this dashed line. This is very close and is a very good approximation here, and not only the magnitude but also the shape. In addition, we also know that we also compare the CDCC4 with the CDCC ground state. CDCC ground state means the kind of nine-less recovery is a one-step process, did not through this continuous state, only using the ground state component. So this is very close to the full CDCC solution here. And also this is a energy, this is for only one energy of lithium-6 on bismuth, and this is energy of the deuterium on the bismuth in this breakup calculation. Here we show this energy of the lithium-6 with different energy and integrate the cross-section of this one, and compare the integrated cross-section with the CDCC, with the CDCC ground state, with the CDCC4 calculation, or the DWB with CDCC4 calculation. And here we all confirm again, this is a very good approximation. DWA is a very good approximation to the CDCC wave functions. The circle is this energy, we put it here. And in addition, we also say this 9-lines breakup is a kind of a mixture of the one-step and two-step processes. This ratio here, CDCC ground state to the CDCC4 wave functions. So in that, for the lower energy case, all the income fusion is kind of transferring to the continuum. When the energy increasing, there is some kind of component of breakup fusion. So in summary, I give a very short summary here. We studied the lithium-6 induced reaction. This is a lithium-6. And for the inclusive breakup means only the upper particle escaped. We don't know what happened with the left. So in addition, we also find the reaction mechanics for the fusion suppression. Also, we're discussing about the reaction parts for the income fusion or the 9-lines breakup. So in the future, in principle, we need to find how to extract the income fusion cross sections. Right now, we only studied 9-lines breakup, but we also need to find out the model to income fusion, not only for the deuterium case and also for the lithium-6. For the deuterium case, this is a very widely application for the surrogate reaction. And also we need to apply the Eastman observation model for no co-out reactions to verify the semi-classical model. So more detail you can find in Angela's talk. And also, in addition, we can also need to study the ascendancies of the two-body interactions to see how it changing the final result. Okay, thank you.